algorithms. First of all, any questions about the last lecture, because that was a kind of experiment to leave part of the slides to study yourself. I gave an introduction to these linear recurrences and matrix recurrences, and the basic idea was quite simple, but there were some special cases that you were required to study. Did any of you encounter some problems with or without looking at the slides? No? Is everything okay with the lab course? No problems so far? Okay. Then today I would like to give you an introduction to sorting methods. First of all, we will discuss an exercise pertaining to these linear recurrences, and then we start with studying sorting by merging. I give you an introduction to, well, let's say the basic facts about sorting, that we are able to provide you, given a limited algorithmic model, a lower bound for any sorting algorithm. And then we start some naive ideas for applying parallel approaches to merging approaches, to merging algorithms. We will discover that these naive approaches are not the best we can achieve. We will prove sorting by merging, and then finally we will discuss a particular intriguing algorithm that uses fast merging and achieves a significant speed up compared with sequential sorting. Then we discuss enumeration sort, and finally random quicksort. Well, that's the, well, let's say the superficial treatment of this lecture, overview of this lecture. The basic idea that I would like to convey in this lecture is that sometimes sequential methods are better than parallel algorithms. And that's because by doing something in a sequential way, you can collect information about every sequential part of the algorithm that's executed and use it in the next iteration. In such a sense that you can profit from this information and can speed up your next sequential process, part of the sequential process. And that is sometimes lacking in parallel algorithms. And we will see two examples from it. In it, and that's the naive parallel sorting by merging, where we will discover that using some method for merging two sequences can use too much parallelism, which results in a, well, let's say, rather very bad work time profile. And if you want to improve such a parallel algorithm, you have to find a way to balance the sequential and the parallel time. So we will use of sequential algorithms for a part of the algorithm, and for the rest parallel algorithms, in order to make better parallel algorithms. And the same will happen in the discussion of random quicksort, where we also will discover that you can do very bad things by following a very naive approach to parallelism and trying to do it parallel all over the world. So let's start with our exercise, and our exercise was solving the Fibonacci sequence f1 equals 1, f2 equals 1, fi equals fi minus 1 plus fi minus 2 for I larger than 2. And well, you would like to have an algorithm that computes the nth Fibonacci number fn as efficiently as possible. You know that, well, there are several algorithms for it. In your bachelor classes algorithms, you should have studied at least two variants of this algorithm. There was this recursive algorithm for computing the Fibonacci function, and there was this dynamic programming approach in which you try to compute Fibonacci bottom up. Well, both approaches end up with an algorithm that's super polynomial. What we try to do is to find a polynomial algorithm for computing this Fibonacci function. And the idea is that you rewrite these equations in the form of a linear recurrence. And there it's very advantageous to realize that, well, given a scalar recurrence equation, you can reformat it into a matrix recurrence. And that's done in the following way. And so look at these equations and then realize that you can form the first two of them into a vector containing two components, f1 and f2. And well, take f1, the vector containing f1 and f2, that's a vector of constants, be equal to 1, 1. So that's the starting point of the series. And then you rewrite the remaining ones, so the real recurrence, into a matrix recurrence equation as follows. Fi plus 2 equals Fi plus 2, and Fi plus 3 equals Fi plus 2 plus Fi plus 1. And you do that for I is 1, 2, until n minus 2. Yeah. And then you have captured all the recurrences that can be formed into a matrix recurrence, realizing that this is a vector and this is also a vector, and this vector can be written as a matrix times another vector. And now you are ready to apply your linear recurrence machinery to find the solution, because this is nothing more than what you learned in class last time, yi equals a times yi minus 1, for example. Okay, so this can be solved by realizing that f1 equals 1 and fi plus 1 equals a fi, where fi now is a vector containing two components. That's what we call, if you have studied the slides, a Krylov matrix. So that's a particular simplified form of the general form fi plus 1 equals ai fi plus bi. The bi now equals 0, and the ai's are all the same and now are equal to a. Then from the things we know about how to compute these matrix equations, we know that, well, the time it costs to compute the entries in such a matrix recurrence equal log n times log n, where m is the size of the matrix, the number of rows of the matrix, or columns, and log n is the number of entries of the recurrence. So this is log n times log n, where m is a constant. Log n times log 2 is O log n time. What's the amount of work? The amount of work is log n times m to the power 3, where m is the size of the matrix. So this is log n times 2 to the power 3, is a constant, of course. It is O log n work. Now, some people think that now we have found a solution that requires log n amount of time, so this would imply that we have a logarithmic method for computing the Fibonacci sequence. Well, this is not entirely true, of course. You should realize that this is a linear algorithm, because if you would like to find the nth Fibonacci number, you can code n in log n bits. Yeah? So what is the here the runtime? The runtime should be expressed in terms of the size of this n. You can express n in log n bits. It will cost you O log n time to compute it, so we have really found a linear algorithm for computing the nth Fibonacci. Okay. All other methods will require you at least n or 2 to the power n or even worse, even dynamic programming approaches. So this is really a fast algorithm for computing the nth Fibonacci. So please realize that this trick, so considering a simple recurrence that is not a first order linear recurrence, here you see that Fi is dependent upon 2 preceding entries in the series, always can be translated into a first order recurrence by grouping terms of the recurrence equations together. Here you have Fi and Fi minus 1, you group them together and then you get a first order matrix linear recurrence. You can perform that trick for every such a linear recurrence that's dependent upon more than one preceding entry. And so please be careful if you encounter such a more complicated one, even with gaps or with conditions. Always group them in such a way that you can translate them to such a simple form, and then you can apply your machine. Yeah. Any questions? Okay, so let's concentrate on sorting. And the first idea I would like to discuss is a lower bound for sorting. Well, you might be familiar with it, but then, well, it's a simple rehearsal. I would like to convince you that, well, by using the normal machinery for sorting and, well, let's say standard algorithmic methods, we cannot do better than n log n for any sequential sorting algorithm. And the basic idea is that, well, if you have an arbitrary sequence of n input values, so let's say that you have some vector of inputs, then you should be prepared for n faculty number of possible outcomes of this vector. So the way in which this vector could be sorted could be end up in n faculty possible outcomes for the sorted variant of the vectors. Well, any algorithm for sorting can be conceived, therefore, as a procedure to generate a suitable permutation of its input. Okay. We can model any of such an algorithm by a kind of decision tree, and a decision tree that takes as input such a vector of entries, so it's an input vector x, and as outcome has n faculty leaves. So the algorithm really traverses a path from the input to the output, and any of these outputs should be possible, any of these n faculty possible outputs, that's a sorted variant of the input, should be possible. So we could model such an algorithm as traversing a decision tree. What kind of decisions are made when we traverse such a decision tree? Well, it is a number of binary decisions or binary comparisons that we make. We compare entries in this input vector in order to decide where the resulting position of any component of such a vector should occur in a leaf. That's the final result of sorting. And more in particular, we compare values x less than I or x large, at least as large as I. And if we make such decisions, sequential decisions, then finally, from the top of the tree, we should end in such a leaf. if you make binary decisions, you have a binary tree, and well, there are quite a lot of algorithms, classic algorithms you should be familiar with, that are based on these binary comparisons. Heap sort, quick sort, bubble sort, insertion sort. All of these classic algorithms are essentially based on making binary comparisons. If you have such a binary tree of n faculty leaves and the tree is balanced, then in principle you can compute its depth. And this depth is log n faculty. Well, you know that n faculty is at least as large as n times n minus 1 times n times 2, and then you forget the rest. Yeah. And this, of course, is dominated by n divided by 2 to the power n divided by 2, because there are n divided by 2 entries. So we know that n faculty is at least as large as n divided by 2 to the power n divided by 2. Yeah. So you get rid of the faculty by expressing it as a power. Well, then it's easy to see that log n faculty is at least as large as log n divided by 2 to the power n divided by 2, what we just derived. That's large, at least as large as n divided by 2 times log n divided by 2, and that's at least as large as n divided by 2 times log n minus log 2, by using here, of course, log a divided by b is equal to log a minus log b, and that's n divided by 2 times log n minus n divided by 2 log 2. This can be rewritten finally as n divided by 4 times log n. Yeah? Well, n divided by 4 times log n is, of course, O n log n. Yeah? So we know that log n squared, n faculty for n larger than 4 to the power log 2 is 4, is equal to n log n. So we need at least n log n steps to reach a decision from a given input vector to one of the leaves in this binary tree. Yeah. Okay. So the time complexity of any comparison-based sequential sorting algorithm can't be lower than n log n. So you should have worst cases that indeed require at least n log n steps. So this means that for well, let's say weakly optimal parallel algorithms, we should always look at a factor n log n for the amount of work, because that's the best sequential algorithm that we can imagine for sorting. Okay, well, in fact there are sorting procedures that we can show achieve this lower bound. And a very familiar one is merge sort. And the idea of merge sort is very simple. What you do is, given an array A, you split it in two halves. Yeah? You sort the halves by applying merge sort, and then you simply merge the two sorted halves, A1 and A2, into a completely sorted sequence. So you apply sorting to the two halves, that will result in two sorted sequences, and you merge the two sorted sequences to a complete sorted sequence. Well, what's the amount of time you need? Well, we know that merging can be done in linear time. So if you have a sequence of sorted sequence of m and a sorted sequence of n, then it will require you the O of m plus n for merging the two sorted sequences. And the basic idea is very simple. If you compare two sorted sequences and you want to find a final sorted sequence, then in every step you make, you can compare two first entries in the vectors, of in the arrays that have to be sorted. You compare them, and the smaller of them goes to the final result, and you compare the rest. Yeah? So at any step you make in its merging procedure, you can add at least one element to the final sorted sequence. Yeah? And that means that, well, since there are in total n plus n of those entries, you can do the merging in linear time. Well, what's then the total time complexity of this algorithm? Well, we know that if n equals 1, you can simply return the vector, so that can be done in constant time. And if you have Tn, then you can do the merging in 2 times Tn divided by 2. That's the recursive equation, plus On for the merge sort, and that results in the Tn is O n log n. Well, since we know that you need at least omega n log n, this algorithm should be called optimal. Okay, so this is classic stuff. Now the ideas. If you look at merge sort, then, well, almost everyone will try to do the following in parallelizing this algorithm. That is, of course, doing this step in parallel. In the sequential algorithm, we should do first the merge sort on the first half and then the merge sort on the second half. If we can do it in parallel, well, then for I between 1 and 2, we do a naive parallel merge sort on the first half and the second half. So this is a very complicated expression, just to assure that you have for I is 1 the first half and for I is 2 the second half. And you do these steps in parallel. And then finally we merge them, A1 and A2, and we obtain the result. Well, this is a very bad result. Why? Well, let's look at the first step. It gives you constant time and constant amount of work. Then the second step, Tn equals Tn divided by 2, Wn divided by 2, and then finally the third step can be done, of course, in On amount of time and On amount of work. The recursive equation now gives you T is Tn divided by 2 plus On. And that gives you a total time of On for the sorting. And of course here an amount of work of On times log n. So what we have done in here achieving a parallel algorithm is reducing the time from n times log n to n. That's a very small step. And we see what is particularly bad in this algorithm, and that is that the total time is still dominated by a sequential part of the original algorithm, and that's the T is On. And that we should get rid of. And so, of course, what you can parallelize, of course, parallelize. But sometimes the choices you make can be improved significantly by just applying, paying attention to steps that maybe in the first sight, or in the first look at the algorithm, do not need to have to be parallelized, but deserve it to be parallelized. Here we clearly see from our analysis that it pays to parallelize the merging step too. So, well, our conclusion from this naive parallel sorting algorithm is that we should concentrate on the parallel variant of the merging step instead of well, paying most attention to the splitting step here in the original merge sort algorithm. So, well, let's concentrate on merging. So, our basic problem is if you have two vectors A, M and B 1 to M and let them be sorted, as in the merge sort, then we want to compute the sorted merge C with n plus n entries. And we would like to do that using a parallel algorithm. Well, we know that there is a best sequential algorithm that takes linear time, so our algorithm should, if it is weakly optimal, satisfy the WMN is the O of n plus n. Okay. Well, how to proceed? Well, what we will do, and this is an overview of the rest of the lecture, is the following. First, again, we will apply a naive merging method for merging sorted sequences of length n plus n. And we will discover that, well, the time is okay. We will achieve a significant speed up. Instead of using n plus n, so linear time, now we will use the log of linear, log n plus n. But our work profile is not okay, because now we are using n plus n times log n plus n. So too much work. That means that we somehow, in using our parallel algorithm, we are losing information that a sequential algorithm is capable to use. That's usually an indication if you don't have a weakly optimal algorithm. Well, to get back this information, we applied a divide and conquer method, and we will achieve a weakly optimal parallel algorithm for merging, where the amount of work now is reduced to O n plus n, and the amount of time remains the same. And then finally, we use this idea for parallel merging to achieve an optimal sorting algorithm, weakly optimal sorting algorithm, that uses log square n time. So we can improve our naive parallel merging algorithm that takes O n time to a more involved algorithm that now achieves log square n time. And that, of course, is a much better time profile than we could hope for using this naive approach. Okay, what's the basic idea? Well, basic idea is ranking. And ranking is a very general technique that is used in parallel algorithms in quite a number of applications, so you should be familiar with it and also able to use it in various contexts. The basic idea of ranking is that you take an element and that you try to decide where in a sorted variant of an object the element should occur in the sequence. And so suppose we have a sequence X and we have an element I, then the rank of I in X equals the number of elements in X that is not larger than 1. So the number of elements in X such that X is less than or equal to 1. Okay, that's a very easy definition. And well, if you have now instead of X a sorted array A, then the definition of the rank comes down to a very familiar one. Well, if you have a sorted variant A1 array, A, then the rank of Y in A is simply the maximum of the indices in A at which an element occurs that is less than or equal to 1. So that means that it is the maximum of these indices, or 0, if the element, of course, is lower than any element in A. And that means that we can compute the rank of such an element by simply performing a sequential binary search in this algorithm and achieve this number in log n time. It's simply looking up, well, let's say, the largest index such that the index is less than or equal to 1 in that array. And that can be done by binary search, of course. So, we know now that, well, determining the rank of a simple element in the sequence, if the sequence is ordered, takes you log n time. And now, well, it's one of the exercises that you might be able to solve for me. What happens if this series is not sorted? How much time do you think would it cost you to find the rank of an element in such a series in parallel time? Yeah? But that's an exercise that you might like to solve for next time. So, suppose now we go even further by considering special cases. Suppose now that y itself is occurring in A. So suppose that we would like to find the rank of AI in A. Well, that's very trivial. You simply return its index position. According to this definition, the rank of AI in I is the largest index such that AI is less than or equal to I, and that should be equal to I itself. If, of course, we now assume that we have unique elements in A. Should be careful, of course. Okay. How do we obtain the merge of two sorted sequences? Well, we do it by ranking each element in X in A and in B to obtain its position in C. Now, let's first assume, and again, it might be your task to come up with a solution if this assumption doesn't hold, that both A and B consist of unique values. That's a simple case. Now, the rank of AI in A equals I. And the rank of Bj in B equals J. A and B are both sorted. So, if you would like to determine the position of AI in C, then what you have to do is simply considering its index position in A, that's equal to I, and then determine the rank of AI in B. And that is the largest index of AI in B. So, at this position, I plus the rank of AI in B, you should fill in AI. And the same holds, of course, for B. If you take Bj, then, of course, its index position in B is already J. You add to it the rank of Bj in A, and then at that position, you fill in the element Bj. Okay. There is one error we could make, and that happens in the case that although each of these arrays might contain unique elements, they might have an overlap. If AI equals Bj, then we make a mistake. And let's look at the following example. Why? So suppose that I give you the following sequences, A and B, and now these are clearly sorted, and we would like to find their merge. Here I have their merge. Now let's look at the third element here. It's 11. The index position in the final array, C here, is 6. The cursor is the 6th position. Why? Well, the index position of 11 in A was its index position is 3, and its rank in B equals 3, because there are 3 elements that are not larger than 11 in B. 3, 7, and 9. Well, if you take the merge, then the first position at which 11 should occur in their merge should be 6. So this is okay. But, well, of course, 11 occurs uniquely in both A and B. Yeah? So we should not have a problem. But now look at the two elements 9 here in A and B. If we now apply the procedure for finding the index position of 9 in C, then we should reason as follows. The index position of A2, 9 in C, equals 2 plus the rank of 9 in B. The rank of 9 in B is 3, because it occurs at the third position. So the final position is 5. But the same holds, of course, with respect to B3. B3 in C has a rank 3 in B, and its rank in A is 2. So both occur at position 5. So that means there is one A missing. The first 9 occurs at position 4, is missing in this procedure. Yeah? And what's the mistake we made? Well, we should take into account that if you have doubles, then the definition of the first position of an element in the merged array C, that's derived from an element from A, should be slightly altered. What we should do is we should determine the index position of AI in A by finding, of course, its rank in A, that's I, plus determining the number of elements in B that are strictly less than AI. In that way, you will find the first position at which AI, the element AI, will occur in the final sorted array. So instead of determining the rank of AI in B, which will, if there is also an element in B equal to AI, give you the second position, you should take AI minus 1 in order to ensure that you collect all elements in B less than AI. So in the previous example, we compute the index of the first 9 in C by the following procedure. It's the rank of 9 in A and the rank of 8 in B. And that gives you indeed the index position 2 plus 2 is 4. And with respect to B, well, we do not adapt it, because if we have double elements, you should get the second element in the final array, and otherwise you don't need to adapt. So the index position of Bj in C is simply j plus the rank of Bj in B. Yeah? So with this simple adaptation, we now achieve a final algorithm, and this is your parallel merging algorithm. For y equal n to 1 to n, par do determine the rank of AI minus 1 in B and place it in AAI, and then at the position I plus AAI fill in the element AI. And do the same for B, and then finally return C. Here you have a very simple example. So if I have here the sequences A and B, this is AA, so this is the collection of ranks in B. This is BB, the collection of ranks of B in A, and then you will find the resulting index positions C1 plus 1 for A1, C2 plus 1 for A2, C3 plus 3 for A3, C1 for B1, C4 for B2, and C5 for B3. Yeah. And the final merge is this one. Well, what is the resulting amount of time we need? Well, we agreed upon finding the rank of a simple element by applying sequential binary search. We can do that in parallel for n of those entries. So it now will cost you the O of log m. Why log m? Well, B contains m entries, and that means that you have to do binary search. That will cost you O log n. You have to do it n times, so the amount of work now is n times log n. Okay, for B the same. it will cost you log n. W is m times log n. And the result will be that t equals the O of log n plus m. Well, this of course is a fairly large upper bound, but the only thing we want to make clear is that you can do merging in the log of the total number of elements. And you know that log n is not larger than log n plus log n. The same holds for log n. It's also not larger than log n plus log n. So the total time is O log n plus n. And the same holds for W is n plus n times log n plus n. This is dominated by n plus m times log n plus n, and this also. Okay. So, well, what's the result? Of course, now the time is okay, but the amount of work is not okay. Well, just before the break, before we start to improve this algorithm, now you should have a feeling of what, well, let's say, is a definite disadvantage of using this ranking approach. So, what kind of information are you losing compared to a sequential approach? So how would you, for example, change your sequential approach with respect to the parallel approach? So, look, here you apply for y is 1 to n of those parallel binary searches. Yeah. Now, the array A is sorted, and if you look at the position in which the first element in A should be placed in B, then for the next binary search, you could use only the remaining part of the array B. Because the next element in A is at least as large as your previous element in A. You apply binary search, and now you have an array. You don't need to search for the whole array. No, you can start from the place where you left the first binary search. So the binary searches that you perform have to be performed on smaller and smaller and smaller portions of the array B. Yeah. And so here we are doing too much work. Yeah. At every time we look at an element in the result in the complete array B. Now, in order to improve that, we will look at the technique that's also very general in parallel algorithms, that you, for some part of the work, you use a sequential algorithm, but you try to preserve the information that such a sequential algorithm could use by profiting from earlier sequential searches, by not applying parallel searches to all elements in the array, but only to a portion in the array. Yeah? And that will be the discussion after the break. So how to avoid losing too much information by applying these parallel searches. Okay, let's reconvene at, well, within 10 minutes, is that okay?